All right, so now we're going to talk about a trigonometric form of a complex number. So we're going to have a coordinate plane. Or let's recap what a complex number is first, actually. So when we have something in the form of a plus bi, so we have a real number plus an imaginary number, that's a complex number. So now we're actually going to graph it. And our coordinate plane is going to look something like this. We're going to have the real axis aligned with where the x-axis is. We're going to have the imaginary axis with line up, that's a m, imaginary axis, with where the y-axis would be. So let's go ahead and graph. Let's take 1 plus 2i. So I would go over here, 1, 2, plot the point. That would represent 1 plus 2i. So just to recap, anything in the form of z equals a plus bi in the coordinate plane, we call this the complex plane. Horizontal axis is the real axis, and the vertical axis we're going to call the imaginary axis. And specifically, the distance between the origin and a point that's plotted on the complex plane, we're going to take the absolute value of that complex number a plus bi, and we're going to define that distance as r. So specifically, let's go ahead and graph something. Let's take our example 1 plus 2i. We had that plotted on the real axis and the imaginary axis, and we said that that was here, 1 plus 2i, and now I want the absolute value, the distance from the origin to that point. So we're going to define that as r equals the square root of a squared plus b squared. So very similar to the magnitude of a vector. So I'm going to take 1 plus 4, and that's going to equal square root of 5. So r, the distance from, okay, we're going to pretend it's a nice straight line, from here to here, is radical 5. But then we can create a right angle. Okay, and if we're calling this r, and I was looking for, let's say, and this is a and this is b, because remember a plus bi, and I was specifically looking for those ratios, I could say the ratios of the central angle theta. So let's put theta in here. That cosine of theta of that angle is equal to adjacent over the hypotenuse, and the sine of theta is equal to opposite over the hypotenuse. So if I were solving for a or b, I would say that a is equal to r cosine theta, and b is equal to r sine theta. So we developed this formula based on this. Remember, z, what we started defining in the beginning, we said that z is equal to a plus bi, and we just trigonometrically solved for a. We said that a is also equal to r cosine theta. So I can use substitution and say then z is therefore equal to r cosine theta for a. And we also said that b is equal to r sine theta. So I could say plus I r sine theta. So now I just developed a trigonometric form for a complex number. Okay, so again, let's recap. In the complex plane, the definition of the absolute value of a complex number is given by the square root of a squared plus b squared. And here's another point that's plotted in the complex plane. We have negative 2 plus 5i. The distance from the origin to that point is the square root of 29, the absolute value distance. So let's say that we want to express that now in the trigonometric form. Let's take that same example. We had z is equal to negative 2i, and it was negative 2 plus 5i. And we want to express that in the trigonometric form. So the first thing I'm going to do is I'm going to solve for r. And remember, r is equal to a squared plus b squared. And I'm going to take the absolute value of that. So it's going to be the square root of 29, and that's what we got in the previous slide. And we're going to go ahead and we're going to solve for the angle, because that's all that's missing. So there's a few ways I could do this. If I happen to land on a quadrantal angle, so that's an angle that lies exactly on the x or y axis. So recap on quadrantal angles: 0, pi over 2, pi, 3 pi over 2, 2 pi. If I land there, those are easy, then I can use those angles as theta. But if I land something like negative 2 plus 1, 2, 3, 4, 5i, and this is where the point was, then I can use my trigonometric ratio. Tan of theta, remember, is sine over cosine, or if I'm going back to that triangle, b over a. So in this case, it's going to be 5 over negative 2. Theta is approximately, arctan, put that in your calculator, and it's approximately negative 68.199 degrees. So now we have theta, and I can go ahead and I can express this in trig form. Z is equal to square root of 29 times cosine negative 68.199 plus I sine negative 68.199. And that was in degrees. So that would be the trig form of negative 2i, negative 2 plus 5i. Alright, so just to recap, the trig form of a complex number, z equals a plus bi, is given by z equals r and cosine theta plus I sine theta. Specifically, r can be referred to as the modulus, and theta is referred to as the argument. So here's an example. Write the complex number z equals negative 2i in trig form. Well, when I graph that, there's no real number on the real axis, or 0 is the value that would be expressed there. And on the imaginary axis, it would fall right here. And that's 3 pi over 2. So that was what I was referring to earlier. If we land there, then it's easier just to use those quadrantal angles when we're expressing it. We also need r. R is equal to a squared, which is 0, plus b squared, negative 2 squared. Take the square root of 4, you get 2. So our answer for that is going to be z equals r, which is 2, cosine of 3 pi over 2, plus I sine 3 pi over 2. And that would be the trig form of the complex number. And now let's say I was going backwards. So now I want to write the complex number in standard form. So I'm going to actually go ahead and evaluate for what's in the grouping symbols. Or cosine of negative pi over 3 is going to be a half. And sine at negative pi over 3 is going to be negative square root of 3 over 2. And don't forget I. Then we go ahead, let's simplify 8 to 2 radical 2, and then distribute. So that way I can see that I'm actually going to reduce those 2's. So I'm going to get radical 2 minus radical 6i. So z is equal to radical 2 minus radical 6i. So that's how we would go from trig form to complex form. Now when we're multiplying and dividing complex numbers that are in trig form, I want you to think of the following. So suppose that we're given two complex numbers. Here's the first one, here's the second one. And we go ahead and we multiply them. That means we're going to do r1 times r2, and then we're going to have cosine theta of the first plus I sine theta of the second, cosine theta of the second value, or the 2 goes after there, I sine theta of the second value, and then we're going to have the FOIL. When we start doing that, we start noticing the pattern of those sum and difference formulas that we had talked about before. So therefore, when we're multiplying, what we're going to do is we're just going to multiply the following. So if I have the first complex number times the second complex number that it's in trig form, we're just going to add the two angles together. And when we're dividing, we're going to subtract the two angles together because of the sum and difference formulas. Okay, so now let's take this particular example. So it says to find the product of the complex numbers. So z1 times z2, we're going to go ahead and do 3 times 2 for r, and then cosine, we're going to add the angles. So pi over 4 plus 3 pi over 4 when we're multiplying. Plus I sine pi over 4 plus 3 pi over 4. So we're going to end up with pi. 3 pi over 4 plus pi over 4 is 4 pi over 4, or pi. 3 times 2 is 6. Cosine of pi plus I sine pi. And because we are finding the product, we are going to evaluate for cosine of pi, and cosine of pi is -1 plus I sine at pi is 0, so I end up with -6. That's the product of those two complex numbers. Okay, in this example, we're finding the quotient. So when we're finding the quotient, we subtract, we don't add the two central angles. So let's take a look. So here we're doing z1 divided by z2 is equal to 24 divided by 8, and then cosine of 300 minus 75 plus I sine 300 minus 75 again. And we end up with 24 over 8 is 3. 300 minus 75 is 225 degrees plus I sine 225 degrees. When we simplify that, we're going to get 3 cosine at 225. That puts us in quadrant 3. Cosine is negative, radical 2 over 2. Plus sine's also negative, radical 2 over 2i. Go ahead, distribute the 3. Negative 3 radical 2 over 2. It's always real plus imaginary, so make sure that you break it up. Minus 3 radical 2 over 2i. Alright, so now let's take a look at a trig form of a complex number that's being used to raise a complex number to a power. So basically, let's take z equals r cosine theta plus I sine theta. When we go ahead and we FOIL that out, we're going to get, because it's the same angle, twice theta for, or double angle for both cosine and sine. When it's to the third power and we FOIL this out, we get 3 times theta. When it's to the fourth power, we get 4 times theta, 5 times theta. So this pattern is going to lead to DeMoivre's theorem, which is named after the person who discovered it. So let's take a look at an example. Again, remember, if we have a complex number and is a positive integer, we're just going to take n, we're going to raise r by the nth power and multiply that to the central angle. So now we're going to use DeMoivre's theorem to find 1 plus radical 3i to the 12th power. So we're going to take we need to find r. So first let's find r, which is the square root of a squared plus b squared. So that's going to be 1 plus 3, which equals 2. So now we have r. We're going to raise z to the power of 12, so that means we're going to raise r to the power of 12. Cosine of 12 times that central angle, but I'm going to need tan of theta is equal to b over a, so I end up with radical 3 over 1, and on the unit circle that's going to correspond to pi over 3, so we're going to do 12 times pi over 3, and then plus I sine 12 times pi over 3. So 2 to the 12th power is 4,096. We have 12 pi over 3 for cosine, 12 pi over 3, plus I sine 12 pi over 3. And 12 pi over 3 is 4 pi, so you can just say 4 pi here and 4 pi here. So 4096 cosine of 4 pi plus I sine 4 pi, and cosine at 4 pi is 1. And sine at 4 pi is 0, so I end up with 4,096 as my answer. Alright, so now we're going to find the roots of complex numbers. So remember when we factor, and let's say we have x to the 6th equals 1, it has 6 solutions. So we can break this up, factor it, we get this, continue to factor it, we get this, and then we have 6 solutions and they would look like this. So we have 2 real solutions and the 4 imaginary solutions. So now each of these numbers is a 6th root of 1. So in general, the nth root of a complex number is going to be defined as the following. So I'm going to use this formula. The complex number a plus bi is an nth root of a complex number z when z is equal to u to the nth power is equal to a plus bi to the nth power. Alright, so here are some more formulas that we need to know in order to find the nth roots. So specifically, when we have a positive integer for n and a complex number z is equal to r cosine theta I sine theta, it has exactly n distinct nth roots given by this formula. The nth root of r times cosine theta plus 2 pi k over n plus I sine theta plus 2 pi k over n, where k is specifically the roots that we're looking for, starting at 0 going to n minus 1. Here's an example. We're going to find all 6 roots of 1. So it might help if we rewrite this. We're going to rewrite 1 plus 0i. And then we're going to find the trig form of 1 plus 0i. So if I were graphing it, 1 exists right here. And it's a quadrantal angle, so therefore theta is 0, or 2 pi. So now if I put that in trig form, and don't forget to find r is equal to the a squared plus b squared, so r is equal to 1. So in trig form, this is going to be equivalent. Okay, so here we're going to have cosine of 0 plus I sine 0. So now, I wrote theta. 0. So now that we have the trig form, so that's the first thing we want to do, express this in trig form. So now that I've expressed it in trig form, the next thing I want to do is use the formula, the nth roots of a complex number formula. Remember that was the nth root of r, cosine theta plus 2 pi k over n plus I sine theta 2 pi k over n. So now I'm going to express that in this formula. So because theta is 0, that's going to make this easy. Oh, I forgot to put a plus sign there. There was a plus sign there. And n, we're looking for the 6th root. So wherever there's an n, we're going to put a 6. So 6, 6, 6, and r was 1. 1. So now we're going to simplify that. So the 6th root of 1 is 1. Then 2 pi over 6 is pi over 3. So pi k over 3 plus I sine pi k over 3. And now we're going to go ahead and we're going to find all 6 roots of 1. So if k were to equal 0, I'm going to get this again. Because we're going to get pi times 0 divided by 3, 0. So the first root is going to be cosine 0 plus I sine 0, which that should say 0, not theta. Which gives us what we already expressed in standard form. So this is what we're going to end up with, and we expressed it in trig form. So I know I'm going to get 1 equals 1. Now I'm going to substitute k with 1. So when we substitute k with 1, we're going to get cosine pi times 1 using this formula, which is pi over 3 plus I sine pi over 3. So now let's go ahead and simplify that. And cosine at pi over 3 is a half. And sine at pi over 3 is radical 3 over 2. I. Now we're going to go ahead and we're going to find k equals 2. So cosine 2 pi over 3 plus I sine 2 pi over 3. And at 2 pi over 3, cosine's negative a half plus radical 3 over 2i. Okay, so k equals 3 is next. So that's going to be cosine 3 pi over 3 plus I sine 3 pi over 3. So that's cosine of pi plus I sine pi. Cosine of pi is negative 1 plus 0i. Okay, so now we're going to find k equals 4. So cosine of 4 pi over 3 plus I sine 4 pi over 3. Cosine at 4 pi over 3 is negative a half plus sine at 4 pi over 3 is radical 3 over 2i, and that's also negative. And now lastly, we're going to look for k equals 5. Because we're going to n minus 1, 6 minus 1 is 5. So now we're going to do cosine 5 pi over 3 plus I sine 5 pi over 3. And cosine at 5 pi over 3 is a half minus sine at 5 pi over 3 is radical 3 over 2i. So lastly, if I were to graph all of this on the real and imaginary axis, we're going to start off with 1. That's our first point. 1 plus 0i. Then we had about right here, half plus radical 3 over 2i. And then about right here, I'm trying to make them equidistant. Negative half plus radical 3 over 2i. Then about right here, we had negative 1. Here, negative a half. And this was negative radical 3 over 2i. And about right here, half negative radical 3 over 2i. So it creates a nice circle between all 3 points with 1, 2, 3, 4, 5, 6 solutions. So 6 roots of 1. And we call this the nth roots of 1, or called the nth roots of unity.